Hey everyone, the drifting camera head. Whoa! Alright, volumes, day 3. They're still alive. 37. Okay, so let's do a quick review of the things that you're supposed to know now. Y equals. How about y equals x squared? Yeah, let's deal with this curve and the x-axis. So we're talking about this region. And I want to do a bunch of things with that region. But I'm wondering if you can A, um, A, find the volume when we have cross sections that are squares. Okay, we want side is perpendicular to the y-axis or parallel to the x-axis, and this is the curve y equals x squared from 0 to 2. Okay, give that one a try. And I think we'll also be then talking about part B. We have that same region, but then I still want squares, but I want my squares to go this way. Okay. So please do those two problems and come back when you're done. All right, well, I know that I'm integrating area, and I know that area is side squared. And I know that these slices would be measured on the y-axis, so this is a dy integral. But what's that? I mean, this distance is x, and this distance is 2, and that's my side length. So my side length is 2 minus x, right? Because here we have our x, this little bit here, this whole thing is 2, and our side length is going to be that whole distance minus the x part. Okay, and area of the square, well, that's side squared, so I've got that. And I guess you could say that x equals square root of y. So I could get rid of this and put a square root of y. Or I could FOIL that original x thing out and then replace all the x's with square root of y's. Okay, so I get 4 minus 4 root y plus y. Good. That's side squared. And so I'm integrating y to the 1/2 plus y dy. Now, what about my boundaries for integration? Well, not 0 to 2, but 0 to, what is my value here? Well, the function is x squared, the x value is 2, so I'm integrating from 0 to 4. All right, that's going to be 4y minus 4. This is going to be 3/2, so I need a 2/3 here. Y to the 3/2 plus y squared over 2. And we're going from 0 to 4. Okay, so that's going to be 16. Square root of 4 is 2. 2 to the 3rd is 8. 8 times 8 is 64 over 3, and that's a minus. And then over here, 4 squared is 16, divided by 2 is 8. All right, and then if I plug in that 0, I get nothing. So this is 24 or 72 thirds minus 64 thirds. That looks like 8/3 is my volume. Fabulous. Okay. Now, these, I'm not expecting the same volume, by the way, depending on whether this thing goes around. I'm sorry, this is a footprint. Yeah, I don't expect the answers to be the same for my two footprints. My other footprint, where we're going this way, I know that the side length is y or x squared, and I'm integrating side squared, so that's going to be integrating x equals the integral of x squared dx from 0 to 2. And we get x to the 4th. So our antiderivative is x to the 5th over 5 from 0 to 2. And I get 32 over 5. Yeah, not the same. Okay. So that was 2 days ago. We were talking about cross sections. What about yesterday when we were talking about disks and washers? So if we have y equals x squared, y equals x squared on 0 to 2. And I'd like this region, and I'd like that region rotated about the x-axis. So, and disk or washer, well, the region, there's no gap between the region and the axis of rotation. So I draw something perpendicular to the axis of rotation, and I see that disk. Or I draw it over here, and I still see a disk. I see that the thickness of that disk is going to be measured here. This is a dx disk. I still need pi r squared. I'm still going from 0 to 2, but I need to get rid of radius and replace radius with some x stuff. Well, this radius is the same as my y value, and y is x squared. So r equals y equals x squared, and therefore r squared is y squared or x to the 4th. So my integral by x to the 4th dx from 0 to 2. Yeah, that's it. Not that big a deal. Be even less of a big deal in 2 or 3 more days. Okay. What if we took that region and rotated it not around the x-axis, but around the y-axis? Okay, so we're taking this footprint, and we're rotating that footprint around the y-axis. Well, there is a gap between the axis of rotation and the region, and because of that, I'm going to have an inner radius and an outer radius. And thickness will be measured along the y-axis. It's a dy thickness, and because this is dy, I'm not going from 0 to 4. I'm going from 0 to 2. I'm going from 0 to, what's the y value here? 2 squared is 4. Okay. So how do I find this? Well, I know that's pi big R squared minus pi little r squared. And I can certainly take the pi out. So 4 big R squared minus little r squared dy. All right, well, let's see what we can say about these things. We know that there's an ordered pair here called x, y, where this distance is y, and this distance is x. So I know that little r is x, and according to this, x is the square root of y. In fact, I want little r squared, and that's just y. Good, so I'm going to plug a y in there. All right, now what about big R squared? Well, you know, this is the big circle, and I notice that that distance is 2. If I were to draw my big circle up here, that distance would still be 2. If I drew it down here, that distance would be 2. Now I think big R is a constant, 2. And so big R squared is going to be 4. This is going to be 4. Okay, so pi big R squared minus pi little r squared, great, dy. And so we have pi, antiderivative of 4 is 4y, minus y squared over 2 from 0 to 4. 16 minus 8 is 8 times pi, 8 pi. Don't forget to plug this in. I know it's 0. But just when it isn't 0, suddenly you're going to have forgotten that you need to plug these things in, so I'm going to keep reminding you. All right. Yeah. So, what about this one? Same region, y equals x squared. That's our region. But this time, I want to rotate around x equals 2. Can you set that up? Five. So, it's a dy. The thickness is measured on a vertical measure. So, this is dy. I'm still doing pi r squared for circles. I'm still going from 0 to 4. What's the radius here, though? No, the radius is not x. This is x. This is 2. The radius is 2 minus x. And it's a dy integral, so I've got to get rid of x and put some y stuff in the place. Remember, y equals x squared, and so x is the square root of y. Okay, so that's going to be 2 minus root y. But we want radius squared, so radius squared is going to be 2 minus square root of y squared, which is 4 minus 4 y to the 1/2 plus y. There's my y squared. So my integral, pi 0 to 4, 4 minus 4 y to the 1/2 plus y dy. Okay, that's good. What if I wanted to rotate same region, this region, around the line y equals 4? All right, well, I always draw something perpendicular to the axis of rotation if I'm looking for a washer. Perpendicular to the axis of rotation, I draw, let's do it that way. Draw this in. That's the best. Okay, if you're doing discs and washers, you draw perpendicular to the axis of rotation, and then at each end, I'm going to make a circle whose center is the axis of rotation. All right, I've got a little r here, and I have a big R here. The big R is a constant 4. Even if I'm over here, the big R is still that constant 4. So R is 4. Little r, some people want to say that's y. This is y. This is 4. So radius is 4 minus y for little r. Okay, so pi big R squared minus little r squared dx. Oh, dx, that's right, these slices go this way. So I've got to get rid of this y and replace with x stuff. 1 minus x squared is r. Okay, our formula here, we plug in r, y integral 16 minus little r squared. So I'm squaring both sides here. So that's going to be 16 minus 8x squared plus x to the 4th dx. And I would distribute and combine like terms. I'll get 8x squared minus x to the 4th dx from 0 to 2. Okay, so that's going to be 8 thirds x to the 3rd minus x to the 5th over 5 from 0 to 2, and don't lose that pi. So what do we get? We've got 2 to the 3rd is 8 times 8, 64 thirds minus 32 fifths. And don't lose the pi. You could stop here. 320 minus 96. 320 minus 96 over 15 and the pi. I guess that's 224 pi over 15 units cubed. Alright. So, we can rotate around lots of different things. We could rotate around something like x equals 4. And so now, when I do discs and washer, I'm drawing something perpendicular to the axis of rotation, and at each end, I'm drawing a circle. Look at little r now. That's little r. Well, this is 4, this is 2. Little r is always just a constant 4 minus 2, or 2. But what about big R? This is big R. Well, it's not x. This is x. This is 4. So big R is 4 minus x. Remember, the thickness of this slice is going to be measured on the y-axis. This is vertical thickness. So this needs to be a dy integral. So 0 to 4 of what? Well, big R. Now, if I know y equals x squared, then x has to be the square root of y. So big R is 4 minus root y. 4 minus root y squared minus little r squared dy. And don't forget that pi. These can't be circular disks unless we're thinking about pi r squared. Okay, that's my side there. Yes, okay. I'll say in addition to being able to do these disk or washer problems, we should also be prepared for something like this. You know, so here's y equals x squared. But now this is my region. This is y equals 4. And so, yeah, not that region. Let's just do a couple of quick setups here. Okay. So, if I want to rotate around the y-axis, draw something perpendicular to the axis of rotation, and make that the center of the circle. Great. Y, so radius is not my y, but my x value. At this ordered pair, this is y, this is x. So radius is x. We want to integrate pi r squared dy. This is a horizontal slice. It's thickness is a vertical thickness. So I know that's square root of y. I get here 0 to 4 pi r squared. It's just y dy. Okay. So pi y squared over 2 from 0 to 4. And that's 8 pi. Okay. Now, what if I then take this region and rotate it around the x-axis? Well, my thickness is now a vertical thickness. I can see it being measured on that x-axis. It's a dx integral. There's definitely a hole here. I do see that this is consistent, so I know that all of my outer radii are going to be 4. So my big R is 4. And what about little r? Let's erase some of this stuff. And try again. No, not that. The picture. There, there. And we'll rotate it around here. Okay. So. Okay. So that's the kind of thing I'm looking for. Big R is this distance, constant 4. Here's little r. Now, this distance is y. This distance is 4. Do I need that? No, I don't need that. But I do need this. This is my little radius. Little r equals y. And that means x squared. So, pi big R squared minus little r squared dx from 0 to 2. This is the pair. Nice. And again, it's not the integrating that gives people sleepless nights with these problems. 16x minus x to the 5th over 5 from 0 to 2, and don't lose that pi. Really, this is yeah. This part, not so bad. Getting this done, that's usually the challenge. It's a big reason why we're spending so many days on this topic. Okay, so that's a review of where we've been. Well, now, let's broaden our conversation to shells. Now, about shells. So there are a bunch of cylinders that we're stacking. You've got this, and then you put another one. Can't. Make pause, show you some shells. Yeah. What I'm going to say, though, is a hard washer is almost always an easy shell. Likewise, a hard shell is going to be an easy disk or washer. But this does allow us some flexibility. So let's take a look at what I'm talking about. Y equals square root of x on 0 to 4. And here's our region. Now, remember with disks and washers, we've started by drawing a line in the region to be rotated that was perpendicular to the axis of rotation. Well, with shells, we draw a line in the region parallel to the axis of rotation. Okay, so I want to rotate around that axis. I've drawn something parallel to the axis of rotation. At each end, you draw a circle whose center is the axis of rotation. To draw a circle whose center is the axis of rotation. And in fact, I'm drawing two of those. One at each end of that segment, that line I drew across the region. All right, there's a shell. And you know, we could be looking at an infinite number of shells. We're just stacking shell on top of shell on top of shell, getting bigger and bigger and bigger. Okay. Well, how do we find volumes with shells? Remember, all these problems start off with us integrating area. So what's the area? Well, the area is this thing. I can't even, you've got a cylinder, but really the only thing you're concerned about is this stuff. It has no top, it has no bottom, it doesn't even have a thickness. So if I cut here and I roll this out, that's what my shell looks like before I roll it up to make it a shell. This distance is the height of my shell. This distance is the circumference of that circle. This distance is the circumference of that circle. So this is 2 pi r. So when we talk about integrating area, well, the area of this rectangle is 2 pi r h. And this is a dy. Let's get rid of this green one. Okay. We could have this situation. Where I'm rotating around this axis. So I draw something parallel to that axis. And there's my shell. This shell is dy. This shell, if I measure the thickness of this shell, that horizontal thickness is going to be measured as a dx. I still have 2 pi r h dx. That area is the same every time I do a shell problem. Well, let's see what we can figure out about these shells. Okay. Now, this is the radius. And we know there's an ordered pair here called xy. And this distance is y. So r equals y. And we just love that because that's dy. Okay. Now, what about the height? Well, that's the height. This is x. This is 4. So my height is 4 minus x. But wait, this is a dy integral. So I know that y is square root of x, which means x is y squared. So my height is 4 minus y squared. So what integral do I write? I write 2 pi y times 4 minus y squared dy. And I'm integrating not from 0 to 4, but from 0 to 2. I would pull the constant out, I would distribute the y, and then I would find the antiderivative. Okay? Just want to focus on this setup right now. Here, we have the same shape, we have the same area formula. The boundaries, though, we're integrating from 0 to 4. 0 to 4. And my height is different now. This is the height. Height is my y value. H equals y. And my radius is my x value. Well, that's convenient. X equals radius, but that's good. This is the one I have to get rid of because this is a dx integral. I don't want h being equal to y. I want h being square root of x. So what would my setup look like? Well, I'd be integrating from 0 to 4 to pi. Height is square root of x. Radius is x dx. And so I get 2 pi 0 to 4 x to the 3 halves dx. Yeah, I'm pretty sure I can do that integral. Yeah, look at all that stuff. You know, another reason why we're taking so many days is just so that you can get used to looking at that. Really, that's a huge deal. But especially if those of you moving on to Calc 2, when you do volumes there, same volumes. Yeah, you're getting ready for Calc 2, but it is on the AP exam. So we need it for both. Yeah. Okay, shells. Let's do some more shells. How about this shell? We're talking about square root of x, and this is x equals 4. Well, now I would like my shell, I would like to rotate about x equals 4. Shells rotated around x equals 4. Okay. Shells, I draw something parallel to the axis of rotation. And at each end of that segment, I draw a circle whose center is the axis of rotation. Okay, so there's a sample cylindrical shell. This is the radius. Well, careful, because that's x. And this distance is 4. So what's my radius? My radius is 4 minus x. Okay, is this a dx or a dy integral? Well, if I measure the thickness of this shell, see there it is, that would have to be measured here on the x-axis. This is a dx shell, and the only thing I still need is the height, which conveniently is my y value. Right? This is xy, this distance, the height is that y value. And we know in this problem that y equals square root of x. So h equals y, which equals square root of x. So ours is going to be the integral 2 pi 4 minus x square root of x dx from 0 to 4. And certainly if we tidy this up, 2 pi 4x to the 1 half minus x to the 3 halves dx, feel pretty confident that you could get us from there. Shells. Shells. So what if we took out region? And this time, we went around this axis. This is still our region. I'm still doing shells, so I'm drawing something parallel to the axis of rotation. And at each end, I'm drawing a circle whose center is that axis of rotation. So there's my cylinder. Here's my handy XY ordered pair. Height. This is height. This is x. This is 4. So height is going to be 4 minus x. Well, what about radius? Well, radius is here. This is radius. This is 2. This is y. So what's radius going to be? It's going to be this whole distance. Take away this y value from our curve. So r equals 2 minus y. Have you figured out whether or not this is a dx or a dy integral? Well, this would be the thickness. And that's going to be measured over here. So it's a dy integral, which means we have to replace x with some y stuff. Remember that y equals square root of x, and if we square both sides, x equals y squared. So I'm going to have the integral 2 pi 4 minus y squared and 2 minus y dy. Again, I'm integrating from here to here, and it's going to be 0 to 4. Nice. I'd pull out the constant, I'd do some foiling, and I would integrate. Okay. Let's just do 1 or 2 more, and then maybe a couple of practice problems for you, okay? All right. So here's our square root of x, and what's our region? Here's our 4. But I want to spin about x equals 7. Okay, and I want cylindrical shells. So if I'm doing shells, what do? That's right. Shells, I always draw a segment parallel to the axis of rotation, and at each end of that segment, I draw a circle whose center is the axis of rotation. Okay? Okay. Give it a try. Hey everyone, welcome back. So, we know, since we're doing shells, we have 2 pi r h. dx or dy? Well, if I measure the thickness of this thing, look, that thickness is measured across the x-axis. This is a dx. Okay, so what do we have here? We have cylindrical shells. We know this is 7, this is 4, this is 0. And we know this curve is y equals square root of x. Well, it looks to me like the height of this shell is my y value, which equals y, and therefore square root of x. The only other thing we need is radius. So here's the radius. It's not x. This is x. Remember the ordered pair, x, y? Why is this so hard? Y is how high up I went from the origin to get there, and x is how much over I went to get there. We know that this distance is 7. So r is going to be 7 minus x. R equals 7 minus x. Well, that's great. We've got everything in terms of x's now. Yeah. So the first common mistake here is that people say that this is x. And that's not x. This is x. This is 7. So this must be 7 minus x. Okay. The next thing that comes up is an issue for people. Like they find h and r, plug those values in. Square root of x, 7 minus x, dx. But what about our boundaries against integration? This is a dx integral. And what we're integrating is this region. This region stops at 4. Does not get to 7. This is a 4. We're integrating from 0 to 4. Shell after shell after shell after shell after shell until we get here, and then we stop. This is just 0 to 4. I agree. That axis of rotation is at 7. Doesn't matter. We're going to integrate from 0 to 4. So please be mindful of that. Okay, we're only integrating that bounded region, that footprint. We're not doing everything except that bounded region or footprint. So what about y equals 5? I want to rotate around y equals 5. Well, I guess I should have finished that last problem. So you could check your answer. Well, I'll do it here. We use shells to find the volume when this region of y equals square root of x is rotated around the line y equals 5. Okay, draw something parallel to the axis of rotation. Make circles on either end of that segment that we drew. Okay. We're integrating 2 pi r h. The thickness of this is a vertical thickness, and so I know I have a dy. Okay. R. What's r? Well, that's r. And that's 5. And that's y. So, 5, take away y, gets me r. And it's a dy integral, so I'm pretty happy about that. What about the height? Well, the height in this situation is not x. This is x. This is 4. So the height is going to be 4 minus x. But I don't want x's. I need y's there. So let's square both sides and see that x is equal to y squared. So integrating 2 pi, 5 minus y, 4 minus y squared dy. And these are y values that we're integrating, so we're going from 0 to 2. Okay, so that's going to be 2 pi, 0 to 2, and some foiling here, y to the third, minus 3y, no, it's a 5, minus 5y squared, minus 4y, plus 20 dy. Okay, so we've got our 2 pi rh, so we should be good here just to integrate that. And that's going to be 2 pi times y to the fourth over 4 minus 5y to the third over 3 minus 2y squared plus 20y from 0 to 2. Okay, plugging in a 0, nothing. Plugging in a 2. I get 16 over 4 is 4. 2 to the third is 8. I get 40 thirds. 2 squared is 4. 4 times 2 is 8. Plus 20 times 2 is 40. And don't forget all of that times 2 pi. Okay, that's minus 4. That's plus 36. Minus 40 over 3. 108. 68 over 3 times 2 pi is 136 pi over 3. I think I might want to check that one again. Mostly, though, I'm concerned about your ability to set these up. Yeah, let's have a packet about that soon. Okay. One more. How about this? Will you take y equals x squared from 0 to 2 and using shells find the volume of the solid when we rotate about x equals 0. Okay, nice gentleman. Hey, welcome. So first, the drawing. This is our region. We want to draw something parallel to the axis of rotation. And at each end, I'm going to draw a circle whose center is the axis of rotation. I see here that radius is equal to x, and height is equal to y. These shells are all stacked this way, so we know we're doing a dx integral. It means this y is going to go away and be replaced with some x stuff. So 0 to 2, it's just 2, yeah. 0 to 2 of 2 pi r h dx. I think that's it. And so here we've got 2 pi integral x to the third dx from 0 to 2. And that's going to be 2 pi times x to the fourth over 4, 0 to 2. 2 to the fourth is 16 divided by 4 is 4. 4 times 2 is 8 pi. And so I got 8 pi. I hope you did as well. We used shells here. Now, let's go back and look at disks and washers for this. So look at the same situation. Y equals x squared. Talking about this region from 0 to 2. And now I want to go back and do disks and washers. Well, remember, if we're doing disks and washers, and this is our axis of rotation, we want to draw a segment that is perpendicular to the axis of rotation. That's going to be my little r. And that's going to be my big R. I notice that my big R is always on that line. Big R equals 2. Little r, a little more thoughtful. This is a dy integral. But what I see is that little r is x. But since this is a dy integral, I know that I can't have x stuff, so x is the square root of y. Okay, square root of y. Well, big R squared is 4, and little r squared is y. So we're integrating from 0 to 4. There's pi 2. Oh, no. This is not shells. We do have an inner circle and an outer one. So this is big R squared minus little r squared dy. Okay, big R squared is 4. Little r squared is y. 0 to 4. So we're going to have 4y minus y squared over 2. 4, 0 to 4. 16 minus 8 is 8. And I plug in 0, I get 0. Now remember, this was pi big R squared minus pi little r squared. Don't lose that pi. And there we go, we get 8 pi either way. Seems like a little more work to me. If there's no requirement in the problem, like the problem says, use shells, use washers, whatever the problem says you have to do. If the problem doesn't specify a method, you do either. Again, a hard washer is an easy shell. I do want to take a moment to point out something that some of my dyslexic students might say. Disks and washers and shells. So if I have a dx disk and washer, it's going to be a dy shell. And if I have a dy disk and washer, it's going to be a dx shell. And that could be another way for your brain to sort of figure out, is this a dx or a dy? How do I find the stupid radius here? Don't worry, we still have 3 more days of practicing this. This, though, marks the end of all the volume content. And for for a long time, this would be just fabulous and wonderful if you could do these. And so I think what we're going to do over the next few days is really just practice this some more. You've got all the knowledge, and now we just want to practice it. Practice seeing, practice drawing, practice setting up. I'm less concerned about practicing evaluating. But, this this shell should have the same volume as that washer. Yeah, that's true. All right, don't give up. Keep working hard, and please ask lots of questions. All right, take care, everyone.